Let's take a look at an example problem from Module 9 for ME12 Dynamics. So in this example problem here, we're given this diagram here. And in the diagram, we can see we have a link here from A to B to C, where we have a pivot point at A, a pivot point at B, and we can see the slider at B is traveling along this track, the slider at A is traveling along this track. We have a length from A to B, 0.2 meters. We have a length from B to C, 0.1 meters. And we have this angle here given to us as 45 degrees, theta is equal to 45, and our initial velocity at A, v of A, is equal to 2 meters per second going downward. So in our problem statement, they tell us block A is moving down at 2 meters per second, and they want us to find the velocity of B at 45 degrees. So the first thing I'd like to do is kind of move this diagram by hand. So if I see that A is going down, that means when A goes down, B is going to slide this way along the track. So for my plan of attack, two parts here. The first part, I'm going to establish a fixed XY direction coordinate and draw a kinematic diagram. Then I'm going to express each of the velocity vectors in terms of their I, J, and K components, and then solve for V sub B equal to V sub A plus omega crossed with R of B relative to A. So now that I've read through my problem statement, have an idea of what they've given me, what they're asking me to solve for, what I can take away from the problem statement and from the given diagram, I redraw out my setup page here. I have a simplified version in 2D now of my given diagram. I choose an established coordinate system. I'm going to go with a standard y positive up, x positive going to the right. I have my V sub A here, so A is moving down the negative y direction. I have my B over here, so as A moves down the negative y direction, B is going to be moving over in the positive x direction here. I have my length from A to B is 0.2 meters. I have my initial angle here, 45 degrees for theta. And I have my length from B to C here of 0.1 meters. I have my given V sub A is equal to 2 meters per second. Theta is equal to 45 degrees. And they're asking us to solve for V sub B. So now that we've created our setup page, we have a place we can reference back to if we need any information as we're going through the solution to our problem. So as we begin our solution here, we can see the first thing we want to do is express each of our velocity vectors in terms of their I, J, and K components. We're going to break them down in terms of their components here. Now what we can do is we can go back to our diagram and see that for B, point B, the velocity at B is constrained to only move in our x direction, our positive x direction there. So our V sub B is going to be V sub B in our I hat direction. Now for V sub A, that's going to be moving down in our negative y direction, so this is going to be a negative 2 j hat. And that's from our chosen coordinate system that we picked here, where we said x is positive going to the right, and our y is positive going up. So next what we can do is take a look at our omega AB right here. We can use our right hand rule there to determine it's moving in our positive k hat direction there. So omega AB is omega in our k hat direction. Next we need to do out a little bit of a trig to get our position vector AB. So we draw our trig triangle over here. We have our hypotenuse coming down here that we know our length is 0.2 meters. Then we have our x component over here and our y component there as we go from A to B. And we can see this is our 45 degrees right there. We say, okay, remember the cosine of 45 degrees is adjacent over hypotenuse. Our adjacent is y, our hypotenuse is our h right there of 0.2. So we can plug that in. Cosine of 45 is y over 0.2. Now we can do the same thing. Sine is going to be equal to opposite over hypotenuse. Our opposite is x. Our hypotenuse is a 0.2 meters there. So the sine of 45 is equal to x over our 0.2. Now we can rearrange these and solve for x and y. Our x is equal to 0.2 times the sine of 45. And our y is equal to negative 0.2 times the cosine of 45. So now we can go back up here to our position vector for r sub AB. And we see that, okay, we'll plug in our x component here, which is 0.2 times the sine of 45 in our I hat direction from down here. And our y component here is negative 0.2 cosine of 45 from this right here. And that's in our j hat direction. So now we have our position vector for AB. Now we have our general equation here that V sub B is equal to V sub A plus our omega AB crossed with our position vector R of B relative to A. So we can take all of the stuff we've solved for now and plug this in to that equation there. So we recall V sub B is only in the I hat direction, so that's our v sub b I hat, is equal to our v sub a, well, we have a value for v sub a, which was -2 in our j hat direction, plus our omega b, which we recall is omega in the k hat direction, positive k hat, crossed with our position vector, r sub ab. So there's our r sub ab right here. So we can plug that in from right up top there. Put this in down here. Then we can go through this, do out our cross product here, omega k hat direction times our I hat component here. And we can do our omega k hat times the negative j hat component here, and we can use this little triangle. I crossed with j gives us k, j crossed with k gives us I, and we can see the positive direction here. So use our little cheat triangle here to make sure we get our sign convention correctly. Recall a double negative, pay attention to sign convention, becomes a positive there. So what we end up with now here is one equation with two unknowns. We don't know our v sub b and we don't know our omega. So we need another relationship to make two equations for the two unknowns. So the way we can do this is to separate into I and j components. So we take each of those equations and we want to break them down in terms of their I and j components. So we do that here. If we take that relationship, we can see that v sub b is only equal to our -2 omega times the cosine of 45. And our j components of that equation, it says 0, because this, our v sub b, is only in our I hat direction, is equal to -2 plus our 0.2 omega times the sine of 45 degrees. So we've taken that one equation there for our velocity of b, and we've broken it down in terms of its individual I and j components. And that's our little bit of a cheat, because we had one equation, two unknowns. Now, technically, we have two equations, one for our I hat components, one for our j hat components, or our x and y, respectively. So if we take a look at our j or our y relationship equation here, we can rearrange it slightly here, move this -2 over to the other side here, and we say that 2 is equal to positive 0.2 omega times our sine of 45. So now we look at this relationship here and we see that there's only one unknown, one equation. We can rearrange and solve this for our omega. We see that omega is equal to 2 over 0.2 times the sine of 45 degrees. We can do our math there, and omega is equal to 14.1 radians per second. Or if we come over here in vector form, we can say omega sub AB vector is equal to 14.1 radians per second in our k hat direction. Now we can take that value for our omega and plug it back into our I component of our equation here. So we do that there. We say, okay, for our I equation, we had v sub b is equal to 0.2 times omega. So we plug in for omega with our 14.1 times the cosine of 45. So from that there, we can get our value for our v sub b. So v sub b is equal to 2 meters per second, or in vector form, we know this is only traveling in our x hat direction to the positive direction, according to our chosen coordinate system where x is positive to the right and y is positive going up. So we now have v sub b is equal to 2 meters per second in our I hat direction.